In this video, I would like to introduce the idea of electric potential energy. And we can pretty much guess by analogy what form this should take. So let's compare the electric case to the gravitational case. So the defining property of electric forces so far has been Coulomb's law, which is F equals K Q1 Q2 over R squared R hat. Okay, and gravity had a really similar formula in Newton's law of universal gravitation. F equals G m1 m2 over R squared R hat. And in that case, we also developed the formula for the gravitational potential energy. And I forgot the minus sign. So there's a minus sign there. The gravitational potential energy is minus gm1 m2 over r. Okay, no squared and no vectors because gravity is a scalar. All right, so just comparing the two formulas, we can figure out the analogy with the electric potential energy. So the U electric is going to be, well, the constant out front and the two charges. And then instead of R squared, we just will have R. And indeed, that's the correct formula, which we will derive later. Okay, so one of the things that I want to do is see in what ways the electric potential energy and gravitational potential energy behave the same, and in what ways they're different, because there are some interesting differences here. Okay, so to begin with, let's review what's going on in the case of gravitational potential energy. Okay, so if I plot U-grav as a function of r, then what we get is just this hyperbola in the negative quadrant here below the axis. Okay, and some of the important features here are that, first of all, the energy goes to 0 as r goes to infinity. So when two objects are very far away, the energy between them is 0, and we can essentially ignore faraway objects, which is a nice feature. Another feature of gravitational potential energy is that we kind of live in a really small range here near the radius of the Earth. In our everyday experience, we never get very far above or below the surface, and so everything that we experience is basically just in this really small region near the radius of the Earth. Okay. Another kind of peculiar feature at first that turns out not to matter is that the gravitational potential energy is always negative. It's never positive. It can get close to 0, but it never quite reaches 0. But that's okay, because we're only ever interested in changes in potential energy. So since we only care about the change in energy, that doesn't actually affect anything. In fact, we found that we could even add some constant to the gravitational potential energy, and then when we take the difference, the constants will cancel out. So if we insisted on having positive energy, we would just add a constant, but that would in fact only complicate things rather than make them simpler. Okay, so in the case of electric potential energy, we have a formula that's very similar. One difference is we don't have that minus sign out front. So in the gravitational case, we had a minus sign. In the electric case, we do not. However, the charges can be positive or negative. So let's consider the case where we have electric potential energy between a positive and negative charge. So if one charge is positive and one is negative, then the product of the two charges is negative. And then we're going to get the exact same shape that we had before, this hyperbola shape. Okay, so we still see that u goes to 0 as r goes to infinity. So that much is the same. We notice that the energy is highest when the particles are far apart. And the energy is lowest when they are close together. Okay, so what that means is that if two particles start out far apart, and one's positive and one's negative, as they move closer together, they will speed up because the potential energy is lower, which means the kinetic energy will be higher. So essentially, they are accelerated towards each other, which is the way that we show attraction. Okay. It makes sense that we have attraction in gravity and also between opposite electric charges. That's what we expect. Okay, so the behavior of two charged particles is very similar to the behavior of two masses being gravitationally attracted to each other. Okay, but now let's consider what happens if we have the electric force between two particles of the same charge. So we have electric potential energy still, but this time we'll have either plus plus or minus minus. Okay, so this time we get a positive hyperbola like this. Okay, because the product of those two charges is going to be positive if they're both positive or both negative. Okay, so here we get some different behavior. Here we see, for instance, that although the energy still goes to zero far away, we have the energy is lowest when they are far apart, and the energy is highest when they're close together. Okay, so what that means is that if I have two, so let's say, positively charged particles that are very close together, as they move apart, potential energy will decrease, which means that kinetic energy will increase. Okay, so they're going to accelerate apart in this case. All right, so the way that the graph shows that the two particles are repelled is because the potential energy is lower when they're far apart. Okay. Interestingly, we do still see that the energy goes to zero when they're far apart. So no matter what the charges are, we can ignore things that are very far away. So that's a nice feature of both of the cases, whether the charges are the same or different. We can only focus on things that are nearby.